Okay, guys, I want to talk to you about engineering and how simple engineering really is. Excuse me for coughing. Engineering is about predicting failures based on your load applications. So you try to predict the failure and where it would happen, and then you try to counteract that failure. Counteracting that failure, you then try to predict whether your counteractions created a new load path to failure. You try to foresee the failures before they happen, such as wind loads, dead loads, live loads, creep, which is just a slow movement towards failure, which means you missed it. Let's look at my beautiful little artwork here that I created using boulders. I love boulders, right? So it looks like it's going to fail. It's only pinned on one side to the left, and it appears to be pinned on one side from this angle. It's obviously the forces on here are quite difficult to try to figure out. That's for scale. That's a 6-inch disc. Yet I can put all my load on the edge of this. I can put my load on this. So we now know the load limits of this. It's right about where I am. If I rock my body weight, I create a shock load. Same load, but now the load is now a shock load, if you will, a hydraulic force. I'm trying to make sure you guys can see the movement. I guess we'll look at that, but I'm going to be moving at the same time. Maybe you can hear it. I got to put more weight on it for a second, and then shock load it. So in other words, I lift my body up and then go like that, without even taking my feet off the ground. With my feet off the ground, I can create a shock load. I'm the shock load. My shifting of my body weight becomes the shock load, the hydraulic force. It's still the same weight, right? But yet my weight can create an extra force even though it's attached to this product, this boulder. So these are little forces that people miss sometimes, engineers don't get, they can't visualize. Hopefully that will help you visualize a shock load of it. Just because that load's a dead load doesn't mean it's also it cannot be an increase of a dead load. So let's say my 100-pound self, which I weigh more than 100 pounds, I can actually create more force even though I'm attached to the structure than my 100-pound weight would, as I demonstrated just then, and you guys can find somebody to demonstrate yourself, is that dead loads sometimes can be magnified just by shifting of the dead load. So to help you visualize that, we have a tanker full of water driving down the road. It slams on brakes. The water weight is still the same, but it surges forward. When it surges forward, it has a new force now, and it can cause the truck to drift forward. That's why water tankers and tankers like that have baffles in them to slow that surging effect down. I wanted to share this with you, just a little bit of a thought, and maybe I'll add to it that so engineering is just figuring out the failure ahead of time and then countering it. Now the countering you're doing is just buying time. It's limited. All engineering will fail eventually. It will need maintenance to keep it going, upgrades, etc. Everything wants to go back to ground, to zero, back to level, back to base level, which is the ground. This boulder will not want to sit here forever. Over time, water would erode this part of the structure out right here, and this would ultimately wind up on the ground. And that's through erosion. It's not through gravity, it's erosion. I guess I'll trigger a couple of you on that gravity. So if the laws are correct, everything has an equal and opposite force against it. That means gravity is linear, and therefore linear doesn't make sense. It's always pulling. Gravity is a black hole at that point. A theoretical black hole. It doesn't have a counterforce. This is why I say gravity is a waste to try to add into formulas. So let's use the engineering of this pad. Look at the engineering of this pad and look at nature. Nature says, I don't care that you put 6 inches of stone here. Nature says it wants to put grass from the ground up. That's what nature wants to do. It will find a way. It's beautiful. Don't hate the grass that is coming through your product. Don't hate that you think you didn't engineer it enough. Nature will break it up. Its job because grass's job is to create aeration for the earth, to create a path for water. I think if you look at it in a natural sense or a great creator sense, that you can't mess up the design. That this solidness cannot take place. It must always be ruined, if you will. I know I used a word called solidness. So let's talk about concrete, and I'll terminate the video. So concrete is it's manufactured slabs is what people are doing when they're doing concrete. Manufactured slabs, except for the manufacturer are these contractors who are manufacturing inconsistent slabs, terribly so. And this inconsistency is where your cracks happen because you're a stone aggregate paste, you're walking on it, you're tamping on it, your drying abilities, you're drying it not in the factory, but you're drying it out here in the ambient weather, which is sun on one section, not on another. Your preparation matters, how you're preparing your prefab slab, your manufactured slab, if you will. So think of concrete as installing manufactured slabs, and what's your quality control for that? You put 10 cents in, you get 10 cents out. You can't put 100% in when you cannot put 100% in. In other words, you can't control the sun, the shade here, and just a few feet over, we have a hot spot. Then another hot spot. This is the canopy of this creating this irregular, it would be a regular development of the concrete. Same thing with the truck. You have the concrete going in at 11 o'clock and you've got concrete going in at 1 o'clock. The ground temperatures are different at that point. Do not expect to treat that 11 o'clock and the 1 o'clock concrete the same come, say, 3 hours later. They're not the same. It all needs to be monitored and paid attention to, specifically the temperatures in your initial set. These are perfect. These are manufactured at a factory. These will not crack. I have not found them to crack. You can lay them in the sun, the winter, the heat, the cold, everything. These are proportionately stable. And even with the waves and curves in them, they're proportionally stable. They're not going to fail. Ultimately, they will fail if you put it on tension, but these are 10,000 PSI products. You're going to need about 1,000 pounds per square inch of tension to make this fail. You're not going to get that with a car. I won't get that. You're not going to get that. You can get it with the hydraulic force, as I just explained. I'm going to terminate the video. I just hope this helped you understand a little bit and help you understand how simple engineering can be. That's the simplest form. The worst form is when you try to resolve everything through math. Engineering should not be resolved all through math. Sorry guys, to trigger you guys on that. You need some damn common sense in engineering. That's what we're losing. And that's what we're losing and causing the failure of the bridge. We're now going to, oh yeah, I want to do a separate video on this, but now I'm 8 minutes into it, I might as well do it. So we're now going into artificial intelligence. Artificial intelligence is what, now maybe that's what I'll title the video. Artificial intelligence is what is killing engineering today. It's not really intelligence. It's just programming that idiots become reliable on engineers, and that would be the OSHA doing that artificial intelligence, if you will, trusting the programming. That would also be Denny Pate and using the programming and data of a computer to do it, and lost his intelligence over to artificial intelligence, which can include math. Math is not a substitute for intelligence. Just because it worked out in math does not mean you figured out how to make this work. Obviously, all the engineers missed that FIU bridge collapsed because they all relied on artificial intelligence, which included their math. They forgot to use intelligence.